Welcome, everyone. Today, we're diving into this explainer of the overheat. It's a $19 mini mission specifically designed for 8th grade science classrooms, and it takes place over just 3 class periods. You know, if you've ever struggled to make engineering standards feel real and, well, urgent for middle schoolers, you're going to find this lesson structure absolutely fascinating. So, let's just walk through exactly how this scenario unfolds.
Okay, here is a quick look at our agenda for unpacking this 3-day lesson plan. 1. The flashy slogan problem. 2. Day 1, crunching the data. 3. Day 2, the safety constraint. 4. Day 3, debunking the pitch. And 5. Scaffolding and assessment.
Section 1. The flashy slogan problem, a real-world drone dilemma.
So, picture this. Imagine you're an 8th grader. Your robotics team is gearing up for a massive competition, and you desperately need a new battery for your drone. You're weighing your options, and one supplier, PowerCell, is practically shouting from the rooftops with an ad that screams, longest runtime up to 3 hours, right? Would you buy a drone battery based on one flashy slogan? I mean, it's incredibly tempting. It sounds exactly like what a robotics team would want. But this scenario perfectly captures a core classroom struggle, which is, how do we teach students to actually look past marketing and act like real engineers? And that right there illustrates the pedagogical heartbeat of this entire lesson. The foundational concept these students absolutely need to grasp is the crucial difference between a criterion and a constraint. Okay, so criteria are the things we want to maximize or minimize. In our drone scenario, we obviously want to maximize runtime and minimize charge time. We want the best performance we can get. Constraints, on the other hand, well, those are the hard limits. These are the literal deal breakers. If a design breaks a constraint, maybe it's a budget limit, a weight limit, or, as we'll see here, a safety limit, it is entirely disqualified. It doesn't matter how good it looks on paper. Teaching students to separate those nice-to-haves from the absolute must-haves is the core of this engineering standard.
Moving on to Section 2. Day 1, crunching the data, establishing the baseline.
So on day 1, the teacher hands the student teams this exact raw data table. They aren't just handed the answers, right? They actually have to do the work. They see battery A, B, and C, each with 3 different trial runtimes. Their first task is to compute the average runtime for each battery. But the lesson asks them an even more important question. Why average the trials instead of trusting just one? This explicitly forces students to realize that real engineers never trust a single lucky or unlucky run. Averaging smooths out that random variation. It's really their very first step away from typical consumer thinking and into rigorous engineering thinking. And the result of that math sets a perfect trap. Once those averages are calculated, battery A comes in at 3.0 hours, battery B at 2.8 hours, and battery C at 2.2 hours. Visually, battery A has a very clear lead. It completely confirms that flashy slogan. Most students at the end of day 1 are going to be totally convinced that PowerCell's battery A is the obvious no-brainer choice. After all, it's got the longest runtime, which was their primary criterion. So they leave class feeling super confident they've already solved the problem.
Section 3. Day 2, the safety constraint, the plot twist.
Day 2 rolls around and the teacher introduces new data. Because a real engineering choice has to weigh every single requirement, not just the flashy ones. So they are presented with a strict safety constraint. Any battery that exceeds 45 degrees Celsius under load is immediately disqualified. It literally does not matter how long it runs. If it gets hotter than 45 degrees, it's out. It's unsafe. This introduces the concept of that hard constraint directly into their decision-making process. Then, the teacher hands out the new data sheet showing the maximum temperatures each battery actually reached under load. And boom, battery A hits 52 degrees Celsius. So the absolutely crucial point here is that battery A, the flashy favorite, the one with the awesome 3-hour runtime, dramatically fails the safety constraint. It is a full 7 degrees over the limit. The students have to immediately disqualify their top pick. It's such a fantastic light bulb moment in the classroom. They suddenly realize that a constraint can ruthlessly eliminate the flashiest performer, because at the end of the day, the longest runtime just isn't worth a drone literally catching fire mid-air. With battery A completely out of the picture, students have to pivot and build their new recommendation. They're left comparing battery B and battery C. Now, both of these actually pass the safety constraint. Battery B is at 41 degrees, and battery C is at 38 degrees. So now they have to look back at their criteria. Battery B runs for 2.8 hours, while C only runs for 2.2 hours.
Plus, their charge times are almost identical, 1.5 hours versus 1.4 hours. By analyzing all this data together, students figure out that battery B is actually the best overall performer. It safely meets the constraint while giving the strongest performance on the desired criteria.
Section 4. Day 3. Debunking the pitch, exposing the math.
Just when the team thinks they have the whole shebang figured out, the pushy sales representative from PowerCell makes one last-ditch effort to save their sale. They throw out this quote, "Battery A lasts 20% longer than battery B. Don't settle for less runtime." And it's a very convincing sounding statistic. 20% sounds like a massive performance upgrade. But the lesson challenges the students to judge this claim using the actual data before they commit to their final written recommendation. The students have to actually do the math. They take battery A's average of 3.0 hours, subtract battery B's average of 2.8 hours, and divide by 2.8 to find the actual percentage increase. And the result? 7%. When they actually run the math on the averages, they completely expose the exaggerated sales pitch. The real difference is only about 7%, which is nowhere near the claimed 20%. But furthermore, and this is the real test of their learning, even if it was 20%, battery A is still unsafe. They learn that a true-sounding percentage can be completely exaggerated, and even worse, it intentionally ignores the deal-breaking safety constraint.
Section 5. Scaffolding and assessment, the teacher's perspective.
Now, what makes this mission so incredibly effective is the scaffolding included to help educators actually teach it. You get a full teacher lesson plan, complete with pacing and prep. You get scripted daily playbooks with answer keys. But a major highlight is the inclusion of scaffolded student pages. For learners who might really struggle with a blank page, the scaffolded versions provide a criteria and constraints table and sentence frames. For example, on day 2, a sentence frame reads, "Blank is disqualified because blank." Of the safe batteries, blank is best because blank. The cognitive load of the actual judging stays completely with the student, but the scaffolding helps them structure their engineering argument.
And this brings us right to assessment. The included rubric is highly effective because you are grading the reasoning itself, not just looking for a single right pick. The rubric scores students on 4 distinct areas: analyzing test data, applying the constraint, weighing criteria, and evaluating the final claim. To get a strong score, a student has to explicitly explain why a broken safety constraint outranks the flashiest performance spec. This directly aligns with next-generation science standards, specifically evaluating competing solutions, analyzing data from tests, and connecting to physical science thermal energy standards. It really proves the deep academic rigor hiding behind this fun, engaging scenario.
So we've walked through the entire 3-day arc. We've seen how a simple drone battery purchase transforms into a masterclass on data analysis, constraints versus criteria, and evidence-based argumentation. I just want to leave you with this final question. Are your students ready to catch the overheat? By bringing this framework into your classroom, you aren't just teaching vocabulary words. You are training them to think, calculate, and reason like actual engineers. It's an efficient, highly focused, and incredibly memorable way to master these standards. Thanks so much for joining me for this explainer, and happy teaching.